we will move to our next presenter. She is Shruti Chakraborty from Staffordshire University. Her topic is Roboscoop, investigating the use of a robotic arm in particulate material handling. Over to you, Shruti.
So good evening, everyone. It's a pleasure to be here. I'd like to share my screen to start. So I'm Shruti Chakraborty, and I would like to thank everyone for the opportunity to present my research topic, which is Roboscoop, investigating the use of a robot in particulate material handling today here at this symposium. This research was taken as a part of a master's thesis at Staffordshire University in collaboration with ECAM Lyon in France and Promtech Limited, UK. To begin with, I would like to start by establishing a bit of a motivation and context for the study. So as we all know, in manufacturing industries, bulk material is used and is handled using silos, hoppers, feeders, and big equipment. However, there are many manufacturing scenarios where small amounts of material has to be measured. For example, in the manufacture of animal feed, where small amounts of chemicals has to be added to the recipe, or in the manufacture of tile adhesives, where small amounts of chemicals need to be added to a mixture. In this scenario, operators even today measure these small toxic chemicals and powder ingredients manually using their hands and using small bench scales. So this process is arduous, time-consuming, and hazardous to the operator's health because they are working with toxic materials. And moreover, this is an extremely time-critical step in the manufacture of these products, which are recipe controlled and whose quality needs to comply with government regulations. So the main motivation of our study was this, and the idea was to replace the human and to use a robot arm to measure small ingredients, small powder ingredients. With the advent of Industry 4.0 and the use of robots now to perform many complex and hazardous tasks in industry, robots can be used to perform many of these tasks like palletizing, bin picking, and even navigating inside unstructured environments. But so far, there has not been any implementation or research of a robot arm that can measure and weigh small amounts of powder ingredients. And so this brings me to the challenges and constraints of our study. So one of the main constraints was the space constraint in manufacturing plants. We wanted to develop a robotic solution that is modular and can easily be integrated into an existing manufacturing plant without the need for reorganizing or addition of more equipment, bulky equipment into their plant, because this has a constraint of space and costs for these manufacturing industries, which is always a problem. The second and more important constraint in this study is the fact that the robot is going to be measuring and weighing powder materials, and powder materials have variable flow behavior. The accuracy and repeatability of this process depends on the flowability of the material, and the flowability of material itself is a multidimensional problem. So that means that the flowability of a material can be affected by factors like the shape of the material particles, the size distribution in a specific sample of powder material, as well as interparticle cohesive forces and adhesive forces arising from interaction between the particles and the equipment where they are flowing. So these forces create a lot of problems, and the flowability also depends on the environmental factors where the powder material is being used. There has been a lot of previous research in creation of experimental methods for determining the flow behavior of powder materials. And this is in fact used in the design of hoppers and silos that are commercially used for bulk material weighing. But none of these methods have been standardized for weighing small amounts of material because they are normally just measured by hand by operators. And so this was one of the challenges for developing a solution with a robot. This brings me to the crux of our objectives. So our main objectives was to create a modular solution that can easily integrate into a manufacturing environment. So we have a robot setup such as this one in the previous picture, where a robot arm is literally used to mimic the actions of a real operator to pick and pour the material from one container to other container to weigh the material. In the second objective was to ensure the accuracy and repeatability for a commercial batching process. So we want to ensure that this process can be commercialized, and even if not in the research phase, our objective was to reach an accuracy and repeatability that can be used commercially. Third, we wanted to develop a learning model for the robot because it was, as I established, material flowability is a multidimensional problem. And so the robot movements must adapt with the flowability of a particular material. So we wanted to develop a learning model using data-driven methods that could determine the flow behavior of a material. And then this result would be used to create a robot algorithm that can adapt its behavior depending on the flow behavior of the material. And then this robot algorithm would be implemented on a commercial robot, and the accuracy of the algorithm was tested. So I would now like to present the methods that we used for our study to achieve our objectives. So the methods can be divided into two parts. The first part is the robot setup. That is the setup of the robot that was used for implementing the algorithm. And the second part is the material characterization, which forms a part of building the material model for the robot. So for the robot setup, we used a commercial FANUC collaborative robot arm. It's a 6 degree of freedom robot arm, as you can see in this picture. It was a custom 3D printed scoop was 3D printed and designed and integrated as the end effector of the robot. So as I explained previously, the idea is that there are two containers, an input container and an output container. The robot would scoop material from the input container and pour it out on the output container. And weight feedback would be achieved using bench scales. The bench scales was connected to the robot arm using a PC interface that was running using Raspberry Pi and NodeRED. This allowed the weight communication and feedback communication from the scales to the robot. So, for example, a target measurement was to be set, for example, 35 grams, and the robot would be asked to scoop and pour material from the input container until it achieved its measurement. At the end, when it achieves the measurement, it must return any excess material that is in the scoop back into the input container. That was the setup. For the material characterization and creation of the material model, we used 10 industrial grade materials, as you can see here, and we carried out experiments to calculate the physical properties of the materials. For example, descriptors like the shape, the elongation, the particle size distribution using laser diffraction. Additionally, we tried to calculate cohesive forces, friction forces, adhesive forces using angle of repose and other tests that were available. And all of this data was then, it's a multidimensional database that was created, and we decided to perform unsupervised clustering algorithm on this material database. Now, unsupervised clustering is a type of machine learning problem where material data or any type of unlabeled data is partitioned into clusters. Is partitioned into clusters, and this data is unlabeled. So the data is clustered into different partitions recursively without being told beforehand how many clusters it needs to perform, it needs to form at the end. In our study, we used hierarchical clustering, which is able to show the relationship between two different data clusters and can partition without being told how many clusters that it needs to perform. And this is especially useful because flowability of a material is not a constant, and it can change depending on the database of materials that are being compared. So talking about the results, the hierarchical clustering analysis helped us to give this multi-level hierarchical clustering diagram, a dendrogram, which shows the hierarchical relationship between one material cluster and another material cluster. So as you can see, the materials have been divided into distinct groups. Some materials, the materials on the right that have been grouped together, they showed very good flowability when we performed our experimental tests. And flowability tends to increase from left to right. So the materials, the leftmost materials are the most poor flowing materials that showed very high cohesive forces and tended to stick to the scoop or the container that they were put in. On the y-axis, you have the distance between flowability. What this signifies is the distance in flowability between two different clusters. So the higher the distance, there is more difference in the flowability of those two material groups. And we can see a clear divide between the poor flowing, more or less moderate flowing, and the very good flowing materials right on the end. This diagram, this clustering analysis, along with other classification descriptors like car classification method, which is commonly used in material analysis, helped us to assign each material in a cluster, a material flowability category. So for example, the materials on the right were classified as well-flowing, good-flowing materials, whereas the leftmost ones were poor-flowing materials. Now, to use this data, what we did was we used, for each category of flow, we determined a minimum starting angle of incline for the robot end effector. When the robot is pouring the material in the output container, the only factors that need to be controlled, the only factor that needs to be controlled is the angle of incline at which it pours the material. So the hierarchical analysis allowed us to determine a minimum starting angle of incline for the robot end effector during the pouring phase, and as well as it also helped to determine the rate at which the angle must be changed. For freely flowing materials, these values were very small because because the material freely flows down the scoop, we want to make sure we add more control, and so a small starting angle was used, and the angle was changed at a very slow rate. Comparatively, for poor flowing materials with high cohesion and tendency to stick to the scoop, a high starting angle was used, and the rate at which the angle was changed was also much faster. The algorithm was implemented on the robot. Three programs were created on the robot, one to scoop the material from the input container, one to pour the material, and another one to empty the remaining excess material back into the input container. And this whole process was tested on the robot using 3 materials that each belonging to each of the 3 criteria that we had created. So good flowing, moderate flowing, and poor flowing materials. And a set target weight was given to the robot using the interface. And the accuracy of the process was measured by measuring how closely the robot was able to achieve the given target measurement. The measurements, the results are shown here. A very good acceptable level of variance and standard error was achieved for good flowing and moderate flowing materials. However, for poor flowing materials with high cohesion, we see that there is a lot of erratic behavior where the material tends to stick and tends to overshoot. So for these materials, what was found helpful was to drop the angle of incline for the robot end effector as the robot gets closer to the target measurement. So, and also reduce the speed at which the robot is changing its angle of incline as the robot is closer to achieving its target measurement. In conclusion, what we found was that the proposed algorithm was a good solution in the research phase, and it provided a good control and acceptable level of repeatability for the research phase. Further research is required in this area for actually getting close to and implementing a commercial solution. So, for example, a further research in the area of design of the end effector, and also expansion of the material database and addition of further material characterization tests. But we believe that robotic ingredient weighing is a very novel and very interesting area of research, and we will definitely see a lot of progress in this in the next few years. Thank you for your time, and if you have any questions, I will welcome the questions now.
Thank you for your nice presentation. If audience have any questions, you can raise.
I have one question, Shruti.
Yes.
This end effector part, are you controlling the position as well as the force?
We are more interested just in the position for the moment. The pose will be coming later.
Thank you.
Shruti, I have one question. That material has been completely emptied or not? How you are getting this feedback? You are using that simple RGB camera or RGB depth kind of camera?
In our solution, we did not want to use cameras. The problem with using cameras in this, it is a good solution to use a camera as well. You can use a point cloud, for example. But in the current solution, the one that was implemented, we did not use cameras. We tried to do everything with weight feedback, because one of the other criteria of our solution was to reduce latency. And there can be a lot of latency if you have the camera, weight feedback, and the robot control. So to reduce that, we tried to focus only initially on weight feedback. And we had weight sensors on the scoop and weight feedback from the scales were the only two things that we used for the moment. But in future, we might be using RGB cameras as well.
Okay, for weight feedback, you have also taken the load what motor torque robotic arm is taking in motor.
Yes, we used force sensors at the end effector, force torque sensor at the end of the end effector arm over here.
And one more question, Shruti, you mentioned you use that NodeRED for this Raspberry Pi programming. So
yes.
Can you explain, just tell us the little brief, what is NodeRED in that?
NodeRED is a web-based API, and what it does is it allows you to create simple control algorithms without using a PLC or getting into the nitty-gritty of using PLC or ladder logic. And it is an IoT solution, Internet of Things solution. You can wire together multiple different solutions together. So you can wire together a Raspberry Pi, you can wire motors, you can wire a lot of multiple objects together using NodeRED, and it allows you to easily communicate between them. So it will give you serial communication, PLC communication, and things like that, to protocols like that, without going into using, say, a PLC or other specific equipment. That's the advantage of NodeRED.
Okay, Thank you, Shruti, for your nice presentation.